semiconductor devices. And he has a brilliant CV, so I'm not lengthening the process by reading out his entire CV. So he is in the main company who leads the development of the chip. So you can understand, you will be hearing some of the recent developments that Intel is working at, and he is involved in the characterization and the technology development group of that particular company. So with this brief introduction, I welcome Wriddhi to deliver his talk, and before that, Ohana will felicitate you with a small bouquet.
এটা অফ কোন প্রজেক্টরটা I think actually while it, can you hear me? Or is this one? Oh, I think it's this one. I think, meanwhile it gets started, just quickly interacting with the audience here. So are you all mainly from third year, fourth year, undergrad, second years? Okay. That's good to know. I will try to tone down heavy jargons and high terms. Try to make it a little bit more comprehensive. I think it's set up now. Light technology. Oh. Okay. So first of all, thanks a lot to the department, CRC ma'am, Professor Dr. Joyanta Lahiri, and the GAABESU team, who kind of reached out to me, I think, few months back, and asked me to deliver a presentation on what I personally work on at Intel. To be very honest, it's a pleasure. It's not being long that I was on the other side of the dais. I think 2018 is when I completed my bachelor's from here. It definitely feels great, and a bit nervous to have the faculties who have taught me in my time sitting in the audience seat. So let me get started. The whole purpose, let's not go into the words specifically, But I think the ultimate target that I have today is, after this talk, if even one or two of you from the audience, if they want to pick this as their career path, I think that I will consider as a success, or that would be nice to have. Uh, what I mainly want to talk about here is next gen computing, which is mainly driven by the future of AI. We have been hearing about this a lot, and how the semiconductor device ecosystem fits into this entire scenario, right? Because mostly when we talk about AI, all we talk about is how softwares are being modified and developed every day to kind of sustain this whole AI boom. What are the contribution from semiconductor devices? I don't think we talk about it very often. So that's the main purpose of this presentation, that we are aware how the semiconductor industry is kind of power horsing this entire effort. So, brief timeline of my journey. I completed my BTech in 2018. I think we were the first batch of IIEST Shibpur. I was in Germany in 2017 summer at University at Bremen, where I was funded by the DARD WISE research. I was working as a research intern there, working on quantum circuits. It was pretty fun. In 2022, I mean 2018, actually, I joined University of Notre Dame as a electrical engineering PhD student under Professor Shuman Dada. Completed my PhD in 2022, and joined Intel right away as a research engineer. Back then, I was just a research engineer. Uh, and the group I am from is called TR Front End Transistor Group. TR stands for Technology Research. Earlier, it was known as Component Research, and I will tell you later why components to technology. What is the fundamental difference between these two? Meanwhile, I was in Micron Technology working as a summer intern for 2 summers, 2020 and 2021. So today, I think the stuff that I will be showing you is mostly what I have learned throughout my journey from 2018 to so far on this particular field. So going back to the title, particularly where I talk about next gen computing, I just want to start off with what is computing, or what we understand as computing. Back in 1900s, and this at the very bottom, the few sentences that you see, it's directly copied from Wikipedia on what computing meant back in 1900s. It specifically meant arithmetic calculations, not simple. I mean, not that you could do on a calculator or just an abacus. You needed much more better computing brains, and mostly those were human brains. That's how we used to define computing back in 1900s. The definition of computing has changed a lot if you look like after 1 century. In 2000s, I would say not very early 2000s, but 2010, around that period, the definition of computing has basically come down to face recognition feature that we see in Facebook today. All we see is simple pictures and some squares and rectangles around our faces, but what goes within is this dense network of neural nets, like face nets or VGG face. These are some well-known face recognition models. Those are out there, and finally, they can basically extract the features out of a particular face and can recognize who this particular person is. So that's what computing is. It's basically matrix multiplication, and that's in early 2000s. If we look at today, the definition has kind of spreaded a bit broader. We now have these kind of autonomous vehicles which has to process data real time. Every time, I mean, you are inside a car, every abstraction that you see, it has to detect that, it has to give the proper response to it. Either it has to stop, or it has to accelerate, or it has to turn, depending on what signal it's processing on real time. We all know about Gen AI. I think all of us use ChatGPT on a daily basis now. It's not just ChatGPT. There are multiple other apps and platforms that we use. You just have to instruct it what to do, and it will do it in no time, basically, right? These are kind of computations we do in our regular life on personal levels. What bigger companies or organizations do, if you look at Amazon delivery network, imagine there are 50 nodes around US where Amazon has to deliver their products. There are multiple paths that are possible, but there are certain computation that can find what is the most optimum path with which you have to spend the least amount of cash. We call it the famous traveling salesman problem, but this can go, I mean, if you increase the number of node in this simple optimization problem, the complexity actually increases exponentially. So this is a very simplified version of one of the computing modes that we have today on a larger scale. Now, definition of computing tomorrow, and I think this is where it gets more exciting. During COVID, we have been seeing this particular problem statement of protein folding. This is basically used for drug synthesis. It will basically calculate the or compute the amount of different combinations of chemicals that can produce a particular uh, combination of drug that we need for any part to basically fight any particular virus. And these computations are not easy, as you can understand. These are really hard optimization problems, and with a general computer you might need more than months to years to complete this one calculation. So we need to make sure that we don't take that long, and it's well within a limit of our computing time. And one of the other very exciting perspective is this real-time extensive data computing based sectors, where we are looking at Gen AI powered robots. You have to basically, and I mean, it's for tomorrow, but I think even companies like Tesla are already funding a lot in this particular sectors. So to basically sum everything in a nutshell, the definition of computing has changed massively in last 25 years by itself. And you can imagine it's just an exponential curve, right? So in next 50 years it's going to change in a completely different manner. So till now we have been able to sustain this change of computing paradigm, and in next 50 years or beyond we have to keep on uh, supporting it in the same way. So it's a matter of sustainability. And what fuels this flawless transition from different computing definitions is what I'm going to talk today. So how many of you have heard about Moore's law, if I can ask? I think fair amount. So Moore's law basically says that the number of transistors in a processor chip, and processor chip can be anything, any laptop that you have today. If you open it up, you will find a processor chip. If you look at that processor chip, what Moore suggested back in 1965, if you look at the plot at the extreme bottom left, he basically had 5 data points, and he extrapolated it and took the slope of it, and he said that the number of transistors per processor chip has to double every 2 years. So this is a mere observation, true, but interestingly this has been the case for last 60 years. So it's not really uh, what should I say? It's not just an observation that he had. He had some background to predict it, and that's what Moore's law is. And it has been guiding the industry that how much development is needed from time to time in order to sustain all the computing demands that we have been having for last 60 years. When we say of transistor, I think all of you are pretty familiar with this, right? For transistor, let's think about a simple inverter circuit, and that's comprises of a PMOS and an NMOS. We all know how an NMOS and PMOS looks. I will not spend much time on it. And this is what we call the CMOS technology, right? So what Moore's law kept on telling us, on the x-axis below, you see these are some numbers in nanometers. We call it process nodes. Back in time, these numbers actually meant something. These days, it doesn't. But just take it as numbers we use to denote each technology nodes. So 45 was, I think, I don't know, was back in 2009 or 2010, or maybe before that. From there, currently, or and 14 nanometer was also, I think, 10 years back in 2014. So these are pretty old graphs, to be honest. But the reason I'm showing it is, if you want to really follow the trends, it's easier to follow when it was actually following the rule. So from 45 to 14 nanometer, if you see, the performance kept on increasing. That's the first criteria that Moore's law says, that when you increase the number of transistor in your chip, at the same time it has to give you higher performance, or else it doesn't mean anything. Now, if you just shrink your transistors, if you just scale it, technically you should get higher performance, but in reality, the performance not only just comes from shrinking the transistor, but it also comes from the fact that to sustain that shrinking, you have to keep on developing more engineering innovations, and that's what keep on driving the performance graphs so steeply. If you look at active power, the power has to go down from node to node, or else it's not a viable technology node, it's not a sustainable node. And finally, if you just take a ratio of these two, performance per watt, that has to keep on increasing, meaning for spending a single watt, you have to have higher performance with every node coming. So these are the key product benefits of following Moore's law. And if you just keep on staying in this particular line of doubling transistor every 2 years, this is what we have gained so far, at least 10 years back. The other important aspect of Moore's law that it talks about is reducing the cost, because this is dealing with a industry, with a capital extensive industry. So the cost has to play a role. If we look at Moore's law, the transistor in a single millimeter square, or that the area needed for a single transistor, that is reducing. That you can see from 130 nanometer node to 14 nanometer node, it's more than 20x, that 20x area less that we need for a transistor. But at the same time, to sustain the scalability, or to pay the cost of making such small transistors, the cost per millimeter square is also increasing, because now every time you have to introduce new process steps which cost money. But overall, industry wise, it's still a positive direction, because if you look at the cost per transistor, that keeps on decreasing. And that's the main thrust for Moore's law and for the semiconductor industry. If that plot hadn't been this steep downward, we wouldn't have the kind of devices, the electronic devices we have today. So the cost is what drives the Moore's law mostly. And how to visualize Moore's law, if we look around ourselves, right? Back in day, if you, I mean, I don't know how many of you have heard about Macintosh, but Macintosh was one of the first products, like a desktop product from Apple, which had only like 10 lakhs transistors. And today, the same company, Apple, making iPhones or iMac, or this fantastic product that we call Oculus, it has more than 800 crores of transistors, right, within a small form factor. So that's more important. So what drive this is the scaling. So there is a huge scaling barrier between having the Macintosh with only 10 lakhs transistor to an iPhone with almost 800 crores transistor, but at a smaller form factor. So what drives this scaling barrier is what I'm going to talk about today. And it has never been a cakewalk scaling CMOS. If you look at this particular plot, I mean, I've always liked this plot. This shows that with each technology node, if you start from the extreme left, which is 130 nanometer, and today we are at 5 nanometer to 3 nanometer node, the number of companies working on each node has went down substantially. In 130 nanometer, there was 26 companies making the transistors. Today, there are only three: Intel, Samsung, and TSMC. That basically tells you that this is a very capital intensive industry, and only the companies that has the product to sustain that cost are still making leading edge transistors. So I will now basically break it up into two sections. One is, I mean, if we look at the whole computer, it's made of two different sections. One is the logic, one is the memory. The logic, memory, both are made of transistor, but the logic is heavily dependent on transistors. I am a logic person myself, so I think the talk will be a little bit heavy on logic, but we will touch base on some memory aspects as well as we go at the end of the talk. And when we talk about transistor scaling, there has been, so I think we will just quickly touch base on some of the main challenges that we have faced in the past. And more we move on to the talk, we will see that what we are doing now, starting from where we were, I think, years back. So when we talk about scaling, right, the simplest way of scaling is classical or dimensional scaling. You take your transistor, you just shrink your gate length, which is the distance between source and drain. That's the simplest way of scaling. You can also scale the thickness of your gate oxide, right? That is also a simple physical scaling. But whenever we try to do that, it comes with certain penalty. If you look at the drive current, or which is basically indicator of the performance of your transistor, that is proportional to or inversely proportional to your gate length. So fundamentally, if you shrink your gate length, your drive current should go up. But at the same time, when you shrink your gate length, in order to sustain the leakage, because once you start shrinking the distance between source and drain, there will be direct leakage path between source and drain. So you need to shut that off. In order to shut that off, what you need to do is you need to increase the doping of your channel, or you need to make your gate oxide thinner. In both these cases, you pay penalty in two different ways. If you increase the doping, your channel mobility goes down, so eventually your drive current also goes down. If you thin your gate oxide thickness, which is your TOX, your C inversion goes up, true, but at the same time, you have too much leakage coming from the gate path, because now physically you have a very thin gate oxide through which electrons can just tunnel in the channel. So this is not a sustainable path to keep on scaling, and we have kind of stopped this kind of scaling back in 2003. This is a kind of an example of back in 2020, back in 2002, when there was an effort to make a 10 nanometer LG transistor. The authors, I mean, it's interesting. The authors, you can see Brian Doyle, S. Dada, Jack Cavalieros, Robert Chow. S. Dada was or is my PhD advisor, and rest of them are my colleague currently. So when they made this effort to make a 10 nanometer LG transistor, you can clearly see the transfer and the output characteristics of the transistor itself. If you look at the bottom picture, there is a very poor gate control. Uh, of course, because in order to sustain a 10 nanometer LG transistor, where your source and drain voltage and potentials are completely controlling your channel, you need a very good gate oxide, very thin gate oxide to control that. Back then, they didn't have that. So that's why you see the high VDS curve, the I on I off ratio is merely 10x. And if you look at the ID-VD curve at the top, there is a poor current saturation. So of course, you can't use it as a transistor eventually. So this is what a 10 nanometer LG transistor used to look back in 2002. I do want you all to remember this slide, because later we will come to a similar slide from 2024, and we will see how that transistor looks right now. That was the first challenge, classical scaling. We cannot do it anymore. Second challenge is power wall. What it means is, if you look at your laptops or computers today, they keep on working at 2.4 to 3 gigahertz, right? There hasn't been much improvement in that frequency space. The main reason for that is, if you look at clock frequency at the top left, it's dependent on I over V. It's basically charging a capacitor, the time required to charge a capacitor. Now we cannot scale VDD anymore, because if we scale VDD without a penalty in I on, as you can see from the transfer characteristics on the left, you have to increase your I off significantly, and that will increase your standby power, because your standby power is VDD times I off. So definitely you can scale your VDD to get the same performance, but then your power or your leakage power goes up significantly, and that is not sustainable. So that has been the reason that we have never been able to scale VDD. If you follow this blue curve, we haven't been able to scale VDD beyond 0.7 volt for almost last 10 to 12 years, and we have been operating at the same VDD range. The only way we can scale, and that's what we call the power wall, because we cannot scale VDD, our active power, we have a particular budget of active power. We cannot increase the frequency as well, because if we increase frequency, our active power will go up at the same time. The only way to increase clock frequency without increasing active power is to actually reduce the VDD at match frequency. The only way to do that is with a transistor, something that looks like the blue one, where it's what we call the steep slope transistor. That it at a matched I off, it turns on much faster or at a much lower voltage. Only in that case you can get the same I on at a lower VDD, and you will not have to pay any penalty in terms of active power or standby power. So the solution to come out of this Powerwall challenge is we need a higher gate capacitance, which is we need a better gate control of the transistor so that we can have these kind of early turn-ons in the transistor. We also need to have a high channel mobility, because without a high mobility, you will never be able to hit a high current at a low VDD range. And of course, what we have always said, we need a shorter gate length, because if you put all these in the equation, all this will manifest as a higher drive current eventually. So that's what we need to overcome the power wall challenge, and that's what has been the driving force for scaling the transistor beyond 2003. Uh, After 2003, the era of scaling, we call it the equivalent scaling, because now we are not necessarily scaling it in a physical dimension, but we are adding these technology boosters or performance boosters that can keep on sustaining our higher performance needs. So we had these three main pillars: the stress, the high K metal gate, and the multi-gate FET. I think just for the lack of time, I will not touch base on stress and high K metal gate, though these are pretty interesting technology features. We will just straight jump into the multi-gate feature, because that's what the future is looking like. So I will skip the high K metal gate slides. Let's just move to multi-gate. So what do we mean by multi-gate? I think what you have learned in your textbooks mostly are the planar transistors, where you have source and drain with a gate on top. The gate controls the flow of current between source and drain. Once the gate is turned on, there will be a flow of current. If the gate is turned off, the transistor has to turn off by itself, and there shouldn't be any current between source to drain. So what it means that when you start shrinking physically, your source and drain comes closer to each other. You need a stronger gate capacitance, or you need a stronger gate control in order to control the channel potential only by the gate. The drain and source, not the source is usually grounded. The drain should never be able to control the channel potential. It always has to be the gate that controls the channel potential. Now, on a planar technology, that's hard, because now you have only one gate to sustain that. If you go to a FinFET, which is the second column, you see the channel is surrounded by the gate from three sides. So what it means is your source and drain have to basically fight for getting uh, any control over the channel, because the gate is much stronger now. Though, I mean, one might think that that should be the ultimate case where we should have a pretty good gate control. That was not enough, because if you look at the FinFET, the red is where your gate oxide is, but between those two blue layers, that's the layer which is kind of ungated. So when you start shrinking your gate length, that region will start dominating, and you will start having leakage at that section. So the final solution, or the ultimate solution that we all came up with, that we should look at something called gate all around, meaning now instead of three, your channel should be surrounded by the gate from four sides. Now, the reason that's really fascinating, because now you have the ultimate control over the channel from gate, and you shouldn't expect the drain voltage to take control of the channel in no way, right? So that's the final or the ultimate structure one could have in a multi-gate transistor technology. And that's going to be our present. I mean, our present is mostly FinFET. If you pick any electronic product today, be it any laptop or any phones, it's mostly not mostly, they are all FinFET transistors. FinFET has sustained the scaling for, I think, last 10 years through multiple iterations. I will not go into much details on this space. Basically, the fundamental key message here is to sustain the FinFET technology, what we have done is we have kept on making our fins taller, thinner, and much tighter pitch, so that we can keep on scaling the FinFET technology by itself. But now I think we are at a limit where we cannot scale any physical dimension in a FinFET architecture anymore. As you can see from different technology nodes, 16, 10, and 7, the number of fins has kept on going down. We started with a 4 fin in 16 nanometer. In a 7 nanometer technology, we have 2 fins. Now, we cannot just cut down the number of fins, because then the total drive current will also go down. So that's why for each fin, we have to make it a bit taller, and we have to make the fins tighter to each other, so that we can make it more densely packed. At the same time, we can drive more current through it. But this is not a sustainable path anymore, right? I mean, a one fin transistor would never make it, because it will drive so less current eventually. So that's where there are these near future transistor scaling paths, which we call the nanosheets. In nanosheets, what we did, we basically took a FinFET, we rotated it by 90-degree, and then we filled up the one side which was not gated with another gate material. So how it helps, if you want to just think about these two images on the left and want to take a look at it from a top down perspective, this is how it will look. The red is the FinFET. So if you're looking it from the top, you will see these 4 fins standing next to each other, but the current is only conducting through those fin lines. The white areas in between, that's not conducting anything, right? It's on the 3D plane. The side walls are conducting, but now you are leaving more area which is not conducting any current eventually. So the way to overcome that challenge was to go to this nanosheet architecture, where if you rotate this fin and you make this nanosheet that basically takes the same amount of device layout area, you can conduct current throughout that entire nanosheet. And if you go inside the plane or inside the board here, you have other nanosheets stacked below it. So eventually what you get is, if you follow the plot on the right, for the same amount, like 1f, 2f, 3f, meaning 1 fin, 2 fin, and 3 fin, if you look at the y-axis, which is the total surface area that the current flows through, if you go to nanosheets with a 4 sheet or even a 3 sheet, for the same layout width, you get much more effective width, meaning much more effective current. So that's the flexibility that nanosheet gives us today. And that's why there is a huge drive to move from FinFET to nanosheet. This is an actual image from Stack Nanosheet from IBM. IBM runs a very extensive research fab in Albany, New York, where I think they have done pretty much all the early works of nanosheet transistors. And that's how a nanosheet transistor actually looks. And just to put in perspective, those small sheets, they are of 5 nanometer thickness. So you can imagine how small and how tiny those are. The ultimate advantage of going to a nanosheet from a FinFET is, if you see the electron density color chart, in FinFET, you have most of the carriers on the sidewall of the fin, so it undergoes more scattering through those sidewalls. But if you go to a nanosheet, most of the carriers are actually at the center. That's how the electrostatics work. The carriers are at the center. You can get a pretty early turn on, because now you are turning the transistor on using 4 gates. So you have a superior gate control. And what it means that now you can probably shrink your source and drain distance even more, because now you have a stronger gate coupling. So that's the other advantage of going to nanosheet, that you can keep on continuing the classical scaling. So that's how the roadmap currently looks. This is the Intel roadmap that I'm showing here. Intel 3 is the last product that Intel released. Currently, the work is fully on Intel 18A. Just to give a perspective of how the nomenclature changes, it started from nanometer, it went to sub 10 nanometer, 743, and suddenly it moved to a double-digit number. The reason being that now at 3 nanometer, beyond 3 nanometer, we are moving to an angstrom era. So 10 angstrom makes 1 nanometer. So 20 angstrom or 18 angstrom actually means 2 nanometer or 1.8 nanometer technology node. We haven't named anything beyond 18A. I mean, there are internal nomenclatures, but I think there is no public release of that yet. So what 18A, the Intel 18A product, it will have a nanosheet transistor, as I showed in previous slides. In addition, it will also have this unique feature for the first time in any transistor technology, which is the backside power with power via. So the way a full integrated circuit works, that you have a layer of transistor, and then you also have some signals routing interconnects. As of now, for all the technology node that I showed before, we used to route this signal and power from top side. So if this is your transistor, all your signals will be coming from the top. Now in this particular technology, we have segmented out the power line and the signal line. The signal line will come from the top, as usual. What the power line, which doesn't require much scaled interconnect, that will come from the backside. So the way this helps us is now we can kind of decouple these two separately. That leaves more space for signal routing from top, because now we can design it in a more flexible manner with more space left. And for the backside power delivery, we can actually make those vias or interconnects more spacious and thick, so that we can supply the power more efficiently with a low resistance from those backside power vias. So that's one of the features that will come in Intel 18A, and there has been a huge research and development that went behind this particular feature. And the other companies like TSMC, Samsung, they are also going to implement this in their product eventually. But Intel is the first one to implement this as of now. One question that someone might ask is the plot on the left that I showed before. How do we make actually a transistor like that, which kind of turns on pretty early and then hits the ion at a desired voltage? So this is something that we call a plan B, which is a cryogenic CMOS. So to put it in simple words, if you follow the plot on the right, again with each technology node, the red line shows that for each of those technologies, when operated at room temperature, you see almost 3x improvement from 28 nanometer to 7 nanometer. If you operate those same transistors at lower temperature, which is around 70 Kelvin, you will get much more improvement compared to its room temperature counterpart. There are multiple reasons. At low temperature, you actually get those steep slope transistors. Your mobility goes up at low temperature because now you have less phonon scattering, and there are multiple other advancements that comes automatically when you operate a transistor at low temperature. With all those combined, the best way to read this graph will be that if you pick on 14 nanometer technology, if you just operate a 14 nanometer technology at 70 Kelvin, it gives you the same amount of benefit that a 7 nanometer technology will give you. So basically, this cryogenic CMOS is a path to get kind of 2 node worth of advancement without actually doing anything and just operating at lower temperature. I mean, needless to say, it's not that simple. There are multiple other challenges with operating at low temperature. You have to actually sustain that huge cooling power. You have to keep on operating it at 70 Kelvin for the entire amount of time, which takes a lot of power and cost by itself. So it's not at all a cost-effective solution. But if you look at big servers, they really don't care about power. Performance is what the key metric is, and this has been proven as one of the potential path. Just to put it into perspective, I think Microsoft back in 2020, they took one of their server products and dipped it into Atlantic Ocean. The reason being that in Atlantic Ocean, if there was certain distance from the sea level, that it maintains, I think, around 150 Kelvin, and they showed that they do get advancement in performance also without spending any cooling, because now they're using the sea water as the coolant. So there has been these kind of funny experiments in last few years. What's the future? So till now, what we talked about is kind of near future. The nanosheet technology is going to be on product in 2025 2026 timeline. This is actually future in 2030 or 2032 range, what we are looking at. What we are looking at is rethinking this classical scaling back again, because now we are in a new transistor architecture, which is our nanosheet or nano ribbon. Can we rethink doing classical scaling here back again? So this is the reason I wanted you to remember that 10 nanometer slide initially. This is a paper that me and my colleague Ashish Agarwal we published at IEDM. IEDM is known to be one of the premier conferences in semiconductor devices. It stands for International Electron Device Meeting. The reason it's famous is any new technology that you see on your product, they are first released in IDM or VLSI. There are these two conferences where the technology paper is released and then it goes into the product. So these are kind of prestigious conferences. And this year we published this data where we actually shrunk the gate length to 6 nanometer on a nano ribbon or on a nano sheet transistor architecture. And if you look at the same transfer and output characteristics, see how controlled it is. If you look back at that 2002 paper, you were merely 10x eye on eye off. Here we have a full, I think, 10 to the power 6 or 10 to the power 7 eye on eye off ratio, which looks like a very good perfect transistor. Which basically means that the nano ribbon or the nanosheet transistor has still a long way to go. We can still keep on shrinking the classical dimensions. We can revisit the classical era back again when we move to this nanosheet platform completely. But what's after nanosheet, right? I mean, the expectation is each technology node should sustain the market for 6 to 7 years. So beyond that, what is the path, or what is the direction? So beyond nanosheet, what we have, or the beyond nano ribbon, what we have is what we call the stacked CMOS. So the green and the blue are basically the NMOS and PMOS. Currently, they are right next to each other. You fabricate NMOS, right next to it, you fabricate PMOS. But in stacked CMOS, you want to take the PMOS and want to put it on top of NMOS. So what it means on a layout area basis, it's taking basically half the area. The combined NMOS and PMOS is taking the same area of a single NMOS or a single PMOS. And I think that is more understandable for those who understand the layouts. You basically have a 2D CMOS nanosheet inverter where you have NMOS and PMOS side by side, and then you put that same NMOS on top of PMOS. It basically comes down to a single layout area, and that's what we call the 3D stacked CMOS. Now, there are multiple ways to develop this 3D stacked CMOS. There is path one. There are basically two paths. One is sequential 3D stacked CMOS. In sequential, there are two paths again. The first path is you make transistors in two different wafers. Like you take the bottom device layer, you make the bottom layer CMOS. Then you transfer a layer for the top device, and then you make a transistor on that. That's how this particular transistor looks on the right. We made a silicon FinFET at the bottom, and then we transferred a germanium on top of it, and then we made a transistor out of it. So that's sequential, because you are making two transistors sequentially. So what it means is basically more cost, because you have to repeat the same process twice to make a single inverter. That's path one. Path two is you make the first layer, you deposit basically some interlayer, some dielectric, and then you make another transistor layer on top of that. Here you are also doing the same way as you were doing before. There is a bit of difference in these two approaches. In this particular approach, you are depositing certain layers at a higher temperature, which is around 600 C. Now, when you expose your bottom layer devices to this high temperature, the bottom layer devices will basically degrade by itself, because the bottom layer devices can't sustain that high temperature. In the second path, we are depositing some unique materials which are being deposited at room temperature by itself. So that doesn't degrade the bottom transistors at all. And then you go on with making the same transistor on that top layer by itself. This is an example from one of my papers published in 2020 VLSI conference, where we were depositing a tungsten dope indium oxide as that channel material. and we could deposit it at a very low temperature, I mean at room temperature. So the bottom transistor layer was intact, it didn't degrade, and then we were able to fabricate the transistor on the top layer based on that deposited layer. So that's the second path of, but both these paths are sequential, right? Because you are making the two layers separately. What is more interesting is what we call the self-aligned monolithic 3D stacking. What it means that you don't need to make the transistor separately, but you make a bottom layer and a top layer together, and then you process, or you do the fabrication process at the same time. So that saves you a lot of cost. I will not go into much details, but this is what we call the complementary FET. And this is going to be the next path after nanosheet. So what basically we are going to do is, if you look at the image on the right, those are actually two nanosheets at the bottom and top, but one is NMOS, one is PMOS. We are going to put the NMOS on top of PMOS, as I explained in the initial slides. And this is still more cost effective and more scalable, because now you can design it at a single go. You don't need two different transistor processings and misalignments between those. These will be processed at the same time. So that's why it's more cost effective and more performance efficient as well. And as I said, Intel, Samsung, TSMC, they are the key players, and they have already demonstrated this CFET or complementary FET as their next choice after nanosheet. So probably in 10 years, this is what you are going to see in your product. So that's the summary for logic. The main takeaway I will say is the density. We need basically two things: the density improvement and the performance improvement. In when we talk about an AI hardware, the density improvement can be done through 3D stacking, as I showed. You basically need to put your NMOS on top of PMOS, or as much as you can stack till it's not power efficient anymore. And finally, the performance enhancement that has to come from fundamental transistor improvements, which involves just gate oxides and classical scaling and mobility improvement, these kind of things. I think I will quickly stop it here, because I also wanted to quickly talk about the memory section of it. I will not go much into details. This is the scaling barrier 3, which we call the memory wall. What it fundamentally means is, till now we were just talking about the processors, but we also have a memory in a chip, and there is a continuous data flow between memory to processor and then back and forth, right? Now you can make your processor as fast as you want, but if your memory is slow, effectively that doesn't help you, because then your entire computer is slow. And I think you have already experienced this kind of problems in your daily lives. So fundamentally, what you need is a much better memory which can keep pace with your fast processor, so that your processor is not limited by your slow memory. And I think a lot of you have seen this particular hierarchy of memories. If you're not, wait till your third year till you see this. This basically means that there are different kind of memories, and the top of this triangle is the memory that is closer to the processor. The extreme bottom is the farthest to the processor. Now, here I'm mainly talking about on-chip memories, because that's what is more important for AI hardwares. For on-chip memories, just focus on the green and the yellow bucket, which is the cache part of the memory. For cache, we usually use SRAM, which has been the dominant force. But there are some alternative solutions that has been under research. One of it is the on-chip ferroelectric memories. Ferroelectric is this particular material which you can switch the dipoles in different directions, and it can retain that particular state. So you can get a 1 or 0 depending on which state you have flipped your dipoles to. So you can take these ferroelectric materials and put it in whatever way you want on a transistor, and you will get these different flavors of memories. Um, we have metal ferro fet to metal ferro metal fet, or we also have FE-RAM, which is basically taking a ferroelectric capacitor and putting it on a drain of a transistor, basically like a DRAM, but with a ferroelectric material. But I think the challenge with all these that we have seen is, I mean, true, these are smaller than SRAM, which is very good. That makes it a very ideal candidate to make on-chip memories. The fabrication process is very compatible with the current fabrication process, which is also very good. But the challenges are bigger. All these are much slower than SRAM, which is definitely kind of a huge challenge. They have poor reliability. Basically what it means that if you buy one of these memories today, within 2 to 3 years your memories are going to die. So these has pretty poor reliability challenges, and finally these are not scalable at all. So there needs to be a lot of innovation in materials and process for implementing these ferro into any product. Rather than that, we have this better solution, which is again stacked 3D, but for memories. What it means, if you remember this particular slide that I showed you before, and said that maybe these are not good for logic because sequential logic is not cost effective, but these can be a good candidate for memories, because for memory you will make it after all the logic layers are already made, where most of the cost is. These will require very less cost, and you can actually have it on as back end of line stacked memory. So basically what you will do is, with each layer you will, if you look at layer 1, those are the silicon transistors that you have already made. Now you can basically make multiple upper layers, and you can keep on making transistors on them, which you can use as memory elements. So these are some of the examples of what I particularly worked on in my PhD time for backend of line memories. We have this 2T embedded DRAM. We have ferroelectric FET based on monolithic 3D channels. The fundamental idea for all these memories is basically they are much scaled than what SRAM is today, and they are much faster, because now you are putting them much closer to the logic. More you put the memory closer to logic, faster is your computer. Um, in addition to all these things, you can also have some neuromorphic devices, where the devices are specific to neuromorphic applications. If you're familiar to a particular neural net, there are synaptic weights in each of the neural networks, and those synaptic weights, currently we use CMOS based circuits, but those can be completely replaced by a single ferrofet if you want, and that gives you very good performance and energy metric. So basically the fundamental idea here is that if we are talking about AI hardwares, we need to move away from general purpose hardware to more application specific hardwares, where the task or the workload can be done more efficiently, because the hardware is designed that way. It cannot be a general purpose computer all the time. So I think that's kind of sums up the presentation today. On the logic side, as I mentioned, for density improvement, you need 3D stacking for both logic and memory. For performance enhancement, you need fundamental transistor improvements. If you want to break the memory wall, you finally need a 3D on-chip memory. And if you are looking particularly for AI hardware, it will need application-specific memories like ferrofet or resistive RAM or phase change RAM or things like this. To again, I think, combine it all in a small nutshell, all these are pretty much work in progress, and you can see the amount of innovations in materials and devices that has gone since this field has bloomed, and there is still much more space and area to do development and innovate. So, and particularly looking at the geopolitical scenario of our world currently, I think semiconductor is going to be a very key element in deciding the power center. And that's why I firmly believe that there is no better time to be a semiconductor technologist rather than now. So I think that's pretty much it. Thank you all for being patient and sitting through it all. If there is any question, I would love to follow up with that.
Spectacular presentation. Thanks, Dr. Chakraborty. I myself being a Chakraborty, I thank another Chakraborty. And any questions for him? Yeah, please, one by one.
So, right, so like since the structure of the gate-all-around transistor and the FinFET, they're very different, especially with the stacking and all. So is the current technology that's being used for fabrication, can that be used for gate-all-around, or is that does it new in
That's a very good question. I actually had the slide. I skipped it for sake of time. Let me. The simple answer is no. The fabrication process changes completely. I don't know. I might use this easily. For FinFET, it looks like this. For gate all around, it looks like this with metal fill. The way we fabricate gate all around is we still make this kind of a structure, but with a super lattice. So for FinFET, this is completely silicon, right? For nanosheet, we make a super lattice of silicon and silicon germanium. Then we follow the same process as a silicon. At a later stage, we come in and then we etch out this CD. So then we are only left with the silicons, and then we do the wrap around. But it's a bit connected to how we used to make FinFETs, but we make the change upfront. If you look at this one, it's a super lattice of silicon and silicon germanium. And later in the stage, you kind of release the silicon germanium out, and then you wrap it around with gate. So that's how we make it.
Yeah, I have one.
Yeah, sure.
Question is like you explained in pretty great detail that like how the gate all around structure controls the channel potential. So I'm interested to note two things. One is the because the T-ball effect is also going to rise with the reduction in the gate length.
Yep.
So you like Intel may have some kind of advanced doping engineering inside. And other question is, what are your thoughts on the contacts? Because if you reduce the distance
pitch.
between source and pin product, so your contact has to also be modified.
Correct. So for Dibble effect, I think since FinFET, we don't use any doping in the channel. Planar, we used to have doping because, as you mentioned, those are the counter dopings, like halo dopings to control the short channel effects. For FinFET onwards, we completely rely on the gate control, and that's why we eliminate any halo doping in the channel, and it's mostly undoped channels, and that helps us because now it can enhance the mobility of the channel by itself. So on the FinFET side, the Dibble was mostly controlled by the tri-gate. And also the other knob to control the Dibble and FinFET is how thin you make the fins. If the fins are thin, then the gates from two sides they can couple easily. The same approach goes into nano ribbon. In nano ribbon, again we rely on gate, but at the same time, if I show you this paper that we just published, yep. So here you see 3.1 nanometer. In this paper, actually, the thinnest we have is 1.7. So the paper here was actually about how do we scale the body thickness. So if we scale the body thickness, that will also control the Dibble. So yeah.
You modulate the electric field.
Correct. So the way to control Dibble in nanosheet, that will have again the same knobs. Gate is the primary knob. The secondary knob is we can keep on thinning the body thickness till we get hit by the mobility of the thin channel. So that's how we take care of Dibble. Your second question was on contact. Contact is I think the biggest problem of all. The moment, so there are two ways to deal with contact, or I mean more than contact, I would say pitch scaling. The way to deal with pitch scaling is you can keep on shrinking your gate length and make more space for the contact. That's one way to do it, but that's not really sustainable. Eventually you need a good contact material on your source drain, and also you need a high doped and low resistance source drain by itself. That's what consists your entire source drain resistance. The hardest part is the interface between I mean, if I have to just draw, say these are your nano sheets, these are your source drain epi, and this is where you're putting your contact. The biggest challenge is at this interface, because at that interface, doesn't matter how you grow it, there will be some oxides, some other contaminations, which will always kind of hit your that interface resistance. It will also cause challenges like pinning, because you can keep on changing the metals, expecting it will have different work functions, but eventually it will pin to the same level. So I think the way we at least try to overcome this challenge is by having much more sophisticated tooling. so that we have that interface as clean as possible. There are multiple treatment that goes in before we put the contact metal.
Do you do any kind of passivation?
We do that, yes. Yeah, we do that. So yeah, the key is to make that interface as clean as possible through pre-treatments or pre-anneals or whatever helps. Yeah.
Any other question? Yes.
So, what specific technical skills or project experience do tech companies like Intel or others expect in a student at the undergraduate college level which will help us crack jobs or for pursuing higher education in the field of AI hardware?
That's a good question. So and again, this is my personal opinion. If you really want to play in the big league, where like you are at the forefront of development and research, you do need to have a technical degree in masters and more preferably PhD, especially on hardware sides. On hardware, I think more you specialize in particular fields, you will get more exposure in the big leagues. Not only just Intel, Samsung, or TSMC, they are just looking at the fabrication part of it. You can also think of companies like Facebook, Apple, or Google, who are actually designing the AI hardwares. These are still kind of supporting that development, right? Because today Google can design whatever they want that sustains or that supports their demand for the particular AI hardware they are looking at, but they cannot make it until the transistor fundamentally delivers that performance, right? So these are two different paths. But if you do want to be in that game where you are at the forefront, you definitely need a PhD, is what at least I have seen in my experience. Now, from a bachelor's level, to be very honest, I always had interest in semiconductor device physics, but it's not that I knew most of it when I was in undergrad. My undergrad thesis and my undergrad projects were mostly device related, but not transistor specific again. So it was all that I developed during my PhD. For you can definitely start it from undergrad level. Nothing is stopping. Today there are much more materials available on online or in anywhere else that you can start developing these knowledges. But I think having a master's or a PhD will definitely help you to kind of phase out that entire knowledge space. Like I mean, to be very honest, the only way to learn transistor is when you measure one. So unless you get that opportunity to measure a transistor that is freshly coming out of fab, you will not really get the feel of how to interpret that data or how to understand that physics better. That's the best way to learn, probably.
Any other questions? No question from the backside. You are learning analog circuits now, doing some fascinating things on devices. Not curious.
One question regarding you said about that in the memory stages we use deep learning and neural networks. So can you exactly more elaborate how it is being used in that?
So in I think so if you just look at neural networks, right? I mean, it's basically matrix multiplication, right? Something like this. Like when you do the optimization in a backpropagation algorithm, you have these different weights, you have different inputs, you multiply this weight matrix with input matrix, you get an output matrix, you compare it with your known data, and then you feed back and you keep on updating your weights. So eventually this is a vector matrix multiplication. Now, in current scenario, how we do this is through CMOS circuits. It needs a 60 SRAM, 60 means 6 transistor SRAM with multiple other resistors and capacitors to make each of these weights. The way we can use AI specific hardware is ferrofet. It requires a single transistor. It's just this dielectric material. Instead of being a dielectric, it's a ferroelectric. It has a very unique property that if you apply different amplitude voltage at the gate, it will support different amount of charge. So you can replicate that as different weights. So imagine I want to use this. You have this is what we call crossbar architecture. So this is, say this is I1, this is I2, this is J1, this is J2, and you have a ferrofet in between like this. So you can provide your input from J1 and J2 and so, which will support this matrix. For each of these, you will have these ferroelectric weights, which will support this matrix, and you will have an output which will be supported by Yij. Now, you need to update your weights. So the way the neural network works is you first need to update your weight every time, and then once you learn, then you need to store that weight. So we call it training and inference. So for training purpose, you need to change your weight continuously. It's like a trial and error. You try 2, you see what is the error, you figure out that no, 2 is not good enough, you change it to 2.5. You again calculate that what is your loss function, you update it to say 3. But now you figure out that no, 3 is too much, so you need to come back. So you need to re-update it to 2.8. So these weight updates can be done very efficiently using ferroelectric,